This video will be a follow along to do some practice problems on Taylor and Maclaurin series. All right, let's get started right away. Problem number one, verify that the Maclaurin expression for f of x equals e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus so on and so forth, and show that the Maclaurin series for e to the x is its own derivative. So go ahead and try this one first on your own. Pause the video to attempt it, and unpause it to see how I approached it and to see what the solution is. Okay, so let's recall what the general formula for a Maclaurin series is. It's this guy right here. Okay, so to find the Maclaurin series, we got to take derivatives. So this table over here. Okay, so the zeroth derivative is just the function itself, e to the x. Okay, the first derivative, what's the derivative of e to the x? It's just e to the x again. Second derivative is e to x again. Third derivative is e to x again. We evaluate it at the center of the Taylor series, which is 0 for the Maclaurin series. Okay, so e to 0 is 1 all the time. Okay, so the term-by-term representation is the nth derivative at 0, so that's 1 plus x to the 0 over 0 factorial plus 1 x to the first power over 1 factorial plus 1 x squared over 2 factorial plus 1 x cubed over 3 factorial, so on and so forth. And this is clearly aligned with this guy up here. Okay, now to answer the second part, to show the Maclaurin series of the exponential function is its own derivative, we just differentiate the Maclaurin series representation. Remember, we can differentiate and integrate power series. Okay, so we differentiate this guy. What do we get? Derivative of 1 is 0. Derivative of x is just 1. Derivative of this, we need the power rule, so it'll be 2x over 2 factorial. Power rule, 3x squared over 3 factorial. Power rule, 4x cubed over 4 factorial. 2 divided by 2 factorial, what's that? That's just 1 factorial, which is just 1. 3 over 3 factorial, that's just 2 factorial on the bottom. 4 divided by 4 factorial, that's just 3 factorial on the bottom. So clearly, this is exactly the same as up here, what we started differentiating with, right? So I should put a plus dot 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 here as well, okay? Which is equal to f of x. Okay. 2a, create a Maclaurin series where g of x is cosine of e to the x. So go ahead and try this on your own first. It's a very typical problem, even for typical college calculus class. So we should have the Maclaurin series for cosine of x memorized. This is the easiest way to go about it. Just have it memorized. Either the expanded form or the closed summation form. Closed form in the summation notation. Okay. We can treat it like a function. Instead of x, replace it with e to the x. So either in the expanded form or the summation notation, wherever there's an x, replace it with e to the x. Okay? So we can simplify this by properties of exponents. This is expanded form. And this is the summation notation over here. So this is the Maclaurin series for cosine of e to the x. Okay? Part B, use a 6-degree Maclaurin series to approximate cosine of e squared and explain why the approximation is so horrid. Okay, so go ahead and try this one first on your own. Okay. We're going to use our answer in part A, this Maclaurin series of cosine of e to the x, to help with part B, because we're asked for cosine of e squared. Approximated, okay? So 6 degree means we're going to stop at the x to 6 term. This is the 6-degree term. That's why it's called 6 degree. So using part A's answer, cosine of e to the x, we're going to approximate it with just this. We cut off at the 6-degree term. Okay? By the way, this isn't exactly x to the 6th, right? But we can always rewrite this exponent in a little differently. Then we would get x to the 6th. Okay. Or you can think of it as this power series, and then we replace x with e yeah, E or something like that, right? That's how we found the Taylor series of cosine of E to X, the Maclaurin series. Okay. So you can either, let me go back here one more time. You can either start from here or start from here. I chose to start from here because I assumed that they wanted you to use your answer from part A to answer part B. Okay, so cosine of E squared is approximately this then. Okay, if we put in the calculator, it's negative 128.141. Okay, this is clearly a bad approximation because remember cosine is between negative 1 and 1. So, but we are getting a negative 128. Big error of over 127, right? So why is it so bad? Well, if you remember, this is why we call it the center of the parentheses. That's where the approximation is perfect. So if we get further away from the center, depends on the function, but usually there's more risk of higher error as you get further and further away from the center of the paraseries. What's the center of this paraseries? It's a Maclaurin series, so the center is 0. We're trying to approximate at E squared. Okay, so let me rewrite this a little bit. Okay. So hopefully if you didn't understand this part, let me write it like this. Okay. So x squared 2 factorial plus x to the fourth over 4 factorial plus minus x to the 6th. This is the cosine, right? Okay. Okay, so let me restart this one. If we start with cosine x, which is this guy right here, okay, and we're trying to approximate cosine of E squared. Okay, cosine x this to the 6th degree is this. We're trying to approximate E squared, cosine of E squared, so we plug in x as E squared, so we get this. Hopefully this is more clear now if that didn't click before as I was explaining. Okay, so my bad. That was not clear. Here it is now. Okay. So what was I saying? The power series is centered at 0 here because it's the Maclaurin series. We're trying to approximate cosine of E squared. It's 100% accurate when it's at the center. So cosine of 0 is what? Even without the power series representation. We know that it's 1. If we plug in x as 0, we clearly see all those other terms will go away and we're left with just 1. So you can hopefully see it's 100% accurate at the center of the power series. And as we go further from the center, there's a higher risk for more error. Okay, so usually we want to make approximations really close to the center of the power series. So for example, maybe we want to approximate cosine of 0.01. It'll be a lot more safer to use this. Okay. We're trying to approximate cosine of E squared. What's the value of E squared? It's approximately 7.4. The center is 0 though. So see how far away it is from the center? That's why this approximation is so bad. That's why you get this huge error. It should be between negative 1 and 1, but we're getting minus 128. Okay. This is a conceptual question here. If we really understand the center of the parentheses and approximating functions using Taylor polynomials and all that. Okay. Hopefully this is now clear now if you got stuck on it. You really need to understand this concept. All right, number 3. Estimate the value of square root of 1.3 by using a third degree Taylor polynomial for y equals square root of x centered about x is equal to 1. So before you try this, I want to mention that notice, see, as I was saying, we want to make approximations close to the center of the power series. 1 is the center that we're going to try to find it for. We're trying to approximate 1.3. So you can see this will be a much safer approximation versus that one we just went about. Okay, so go ahead and try this one first now. So we're going to find the Taylor polynomial first. We got to go through the motions of it. We got to take derivatives. So that's this table over here. So we want a third degree Taylor polynomial. So we need to take up to the third derivative. Okay, so that's all this stuff over here, and we evaluate it at the center at x is 1. So you can go ahead and pause the video to check this out yourself. Should be straightforward in my opinion, but definitely if you have questions, you can feel free to leave a comment. Okay. So we find the Taylor polynomial to be 1 plus, we just go through like building the Taylor series, but we stop at this term over here. So it'll be half times x minus 1 to the first power over 1 factorial minus the fourth x minus 1 squared over 2 factorial plus 3/8 x minus 1 cubed over 3 factorial, which we can simplify to this line over here. Okay, so we're going to use this to approximate square of 1.3. So T3 of 1.3 is, you just need a calculator for this, it's 1.14043755, something like that. Okay, now this is just for learning purposes, but if we actually put square of 1.3 in a calculator, it's this much. So look at our approximation, look at the actual value. It's pretty close. There's 0.02% error. That's pretty good. Okay, I say pretty good. It really depends on the application. If you need even less than this error, then it's a bad approximation. So you probably need a higher degree Taylor polynomial to get a better approximation. But it depends on the application and how precise you need it. Okay, number 4, this should be 4a. Let P of x be this guy, be a Taylor polynomial of degree 3 for f of x centered about 2. What is f double prime of 2? So go ahead and try this first on your own. Okay. Let's recall the formula for a Taylor series or a Taylor polynomial. It's this guy over here. The nth derivative at 2, x minus 2 to the n over n factorial. So where does the second derivative term happen? When n is 2. So it's second derivative at 2, x minus 2 squared over 2 factorial. So we got to match this term with some term in here, which we probably want to match it with the second degree term. Okay, so we set this equal to this over here. 3 times x minus 2 squared equals this guy. The x minus 2 squareds would cancel, right? So we can move this 2 factorial to this side. 2 factorial is 2, so f double prime of 2 is 6. This was pretty simple if you were able to think it through. Okay. Part B, same Taylor polynomial. Now they're asking us to use a second degree Taylor polynomial to approximate f prime of 2.1. So go ahead and try this first on your own. Okay. So to approximate f prime of 2.1, we probably need f prime, but we're not even given f. So are we stuck? Not quite. Because recall that we can differentiate and integrate power series. Since P is the Taylor polynomial representation of f, that means P prime will be a Taylor polynomial for f prime. Okay, so we can just find P prime, which is this right here, just do the power of one chain rule. Okay. Now the problem asks for a second degree Taylor polynomial for f prime of 2.1. Conveniently, P prime is already a second degree polynomial, so we don't have to do anything. If we actually, well, this is already a, second degree Taylor polynomial, so it matches the description right there, okay? So we're going to use P prime directly to approximate f prime of 2.1, okay? So P prime of 2.1, we're calling x is 2.1 to P prime, so it will be minus 0.55. Okay, the key idea was, since P is the Taylor polynomial for f, that means P prime is the Taylor polynomial for f prime. That's the idea. Okay, that's it for this problem set. Hopefully it was helpful to reinforce some of the concepts. And hopefully you see that a lot of it is not so much the going through the motions of following some procedures, really thinking through the concepts. All right. Please give this video a like if it has helped you in any way, and hopefully see you in another video as well. Bye.